When we talk about solutions, especially we're talking about things dissolving in water, you have to be a little careful of the stoichiometry and the number of atoms that are being released in each one of these situations. Okay? So if I start with something like this, a sodium sulfate, right? And that's a salt. So I identify it as a salt or as a solid. And I put this into water. What I'm going to get out at the end is a stoichiometric ratio of the sodium compared to the sulfate. Sodium ions, as we know from salt, okay, are going to be plus charged. Okay, so there's a plus charge on the sodium, and we know that they're aqueous. Okay, and the same thing is going to happen to the sulfate. Okay, and this has a -2, and we know that the sodiums that are involved, I've got 2 of them. So I have to put a 2 over here with the solution. Now we all know this from balancing, right? So but when we put this in the concentration terms, the same type of thing happens. So if I have a 0.5 molar solution of sodium sulfate, okay, the stoichiometric ratio of sodium sulfate is 1 to 1 with that of just regular sulfate. Okay? So this is going to be 0.5 molar over here with the sulfate. But because I released 2 moles of the sodium, that means I'm going to have double the amount of ions of sulfate, or sodium, associated with the reaction. So the concentration of this one is going to be 1.0 molar. Now a lot of times, especially in general chemistry too, when we're talking about concentration of ions, we always use a shorthand, and that's to use brackets to identify something that's supposed to be a concentration term. So the way I would say this is to identify the concentration of sodium ion as being 1.0 molar. So anytime you see those brackets, know that you're working with a concentration term. Okay, so working off of that idea, whenever we have a solution, and that solution is something that represents a reaction, we mix 2 things in the solution and we might get a precipitate. Now if we remember our solubility rules, we know that barium and sulfate, when mixed together, make an insoluble salt. So in this case, I take something that's soluble, sodium, something else that's soluble, in this case barium chloride, and I mix them together. So both of these things are aqueous. And what am I going to get out at the end? Right? It's a double replacement reaction, or metathesis. So we've got to swap out both of the anions, or both of the cations, depending upon which way you want to do that. And what I'm going to have here at the end is barium sulfate and sodium chloride. Right? Now, how many sodium chlorides am I going to have? I've got 2 of the sodiums, and I've got 2 of the chlorines. So in this case, I'm going to have 2 of those. And which one of these is aqueous and which one is solid? Well, this one over here is aqueous, and this one over here is solid. Okay? Now we've done this, we identify this and say, yes, this happens because it's a precipitation reaction. The barium chloride is going to, the barium sulfate is going to be the one that falls out of solution as our precipitate. Now we can do some more analysis with this, especially when we want to find out an unknown amount of certain metal or certain anion that are in the solution. And we do this by using something called gravimetric analysis. And what gravimetric analysis is trying to pull out as much of that solid, or as much of that metal or that anion that's in the solution as we can, out of that solution as a solid. Then we can identify by the amount of solid that's left over how much was originally in the solution. Okay, let's demonstrate. So suppose, in a word problem, that I have a solution of unknown sulfate concentration. All right? So I have an unknown amount of sulfate that's in a solution. I've decided that I'm going to add barium chloride to the solution in order to get as much of that sulfate out. So I'm going to add excess barium chloride, and I'm adding it as a salt to the solution. Okay? So adding this to the solution, because it's a chloride, it'll dissolve in the water. To the solution, actually I'm going to add this not as a solid, that might be a little confusing. Let's just do it as an aqueous solution. To precipitate, barium sulfate. I get 3.875 grams of barium sulfate out. Okay? How much sulfate was originally in the solution? Or what was the sulfate concentration in the solution? Let's do that way. Right? What was the original sulfate concentration? Okay? Now the idea here is that because I know that sodium sulfate and barium chloride, okay, when they combine, I get out barium sulfate. I know that if I add enough barium chloride to the solution, I will pull out all of the sulfate that's there as a complex between barium and sulfate. So the mass that I get out here is the sum total of all of that barium sulfate that comes out of the solution, or all of the sulfate ion that was originally in that solution. Okay? So how do we solve this at this point? Okay? Let's throw up. Yes, everybody throw up right now. Ah! Let's throw out a couple of solutions, okay? All right, so how do we want to approach this problem? Well, we've got 3.875 grams of barium sulfate. Now, you've all been trained very well in high school to look for the number, then use that number to try to solve the word problem, okay? It's going to work in this case. So 3.875 grams of barium sulfate. We're going to use this to get what? The moles of barium sulfate. Very good. All right? And since I've been given barium sulfate, and I'm pretty sure there's a periodic table somewhere nearby, I can use the barium sulfate molecular weight to find the number of moles of barium sulfate. Okay? And this is going to give me the number of grams. I wrote moles here, barium sulfate. That should be grams, barium sulfate. I should use this to be able to get the number of moles of barium sulfate here. Okay? Moles of barium sulfate. Right, so what do we get from that? Now that we know the moles of barium sulfate, we can use the stoichiometric ratio of barium chloride and barium sulfate to figure out what the amount of original sulfate there was in the solution. If you look at this, this is 1-to-1. So if I get the moles of barium sulfate, I will know at that point the moles of sulfate that was originally in the solution. Okay? Now I forgot to put one piece of information here, right? And I will solve that here. The original sulfate concentration in 1.0 liter of water. Okay, I forgot to put that there. You can't get the concentration without the volume of solvent, right? So there we go. We can figure out the moles associated with this. So if we do the math, we'll be able to figure it out. So I know that the molecular weight of barium sulfate is 233.37 grams for every mole. Now I've got the grams of barium sulfate here is 3.875. So let me go ahead and write that in. 3.875 grams barium sulfate. Both of those cancel, some moles goes on the top. So we divide those two and we get this number. And we get out 0.166 moles. Okay? All right, is that the right number of sig figs? My calculator is having some fun with me because that's not the right number of sig figs. So 3.875 divided by 233.37, and we get 1.660 moles. Okay? So 4 sig figs listed there. Okay, so 0.166 moles, so that's what my value is over here. Moles of barium sulfate, and over here, because those two are equal, I know that that's going to be the number of moles of sulfate. All right? Now, how am I going to get the concentration of sulfate? Well, I've got moles of sulfate, and I know from original chapters that big M is equal to moles over liters, and M is our concentration term. I've got moles here, right? Number of moles of sulfate. I divide that by 1.0 liters that I've got over here, and my ending concentration is going to be 0.017 moles, because I've got two sig figs here. So my last concentration of this thing is going to be 0.017 molar. Excuse me. All right? That clear as mud? Good. Let's do another example. All right, now in this case, I've got more solutions, and I've got 50 mils of a 0.150 molar calcium chloride solution, and I'm adding it to 18 milliliters of a 0.1 molar silver nitrate solution. How much silver chloride am I going to get? Okay. First thing we're going to do is we've got to write out the balanced equation for this. Okay. So what we're doing is we're adding calcium chloride. That's aqueous, okay? And I'm adding that to silver nitrate. That's aqueous as well, all right? I don't think I left myself enough room, but we'll see, okay? And do a double replacement reaction, okay? I'm going to swap out both anions. And what I get out is calcium nitrate plus silver chloride, all right? This one happens to be solid. Okay, this other one is aqueous because it's a nitrate. We know all nitrates are going to be aqueous. All right, so now we have to make sure that we balance this properly. So I've got one calcium on this side, one calcium on that side, but I've got two chlorines over here and one chlorine over on the other side. So let's balance that. Now put a 2 there for the silver chloride. And I'm going to put a 2 here for the silver nitrate. That balances everything. It even balances the nitrates over here with calcium nitrate. Okay? The ratio here is that for calcium chloride, one calcium chloride is going to react with 2 silver nitrates to give me 2 silver chloride ions. Okay? It's an important stereochemical consequence. At this point now, we want to calculate the number of moles that I've got in each one of these. And I've got solutions for each one of them. All right? So I've got molarity, big M, okay? And I've got milliliters in that case, all right? So my first case over here, this top one, I've got big M is equal to moles over liters, but I want to rearrange this so I just get moles. So big M times L is equal to moles, okay? Now how do I solve that at this point? Well, I've got 0.150 molar times number of milliliters I've got, 0.0500, running into that thing, liters, excuse me, not milliliters, but liters. All right, and that's going to give me the number of moles that I've got. So now at this point, all it is a calculation. Let's do that with the other one as well, all right? And that's going to give me moles. This one gives me moles of calcium chloride. And I want to figure out the number of moles of silver nitrate that I've got. So I've got a 0.100 molar solution, and I've got 18 milliliters. So I convert that to liters. All right? So that's the number of liters that I've got. And this will give me the number of moles of silver nitrate that I have in the solution. All right? So let's do that calculation, and we'll write the numbers in so you can follow along. All right, so right here I've got my two values as far as moles go. All right? Now, which one of these is going to be the limiting reagent? Aha! Concepts from the past are coming to haunt you, right? Limiting reagent. Which one is going to be consumed first in this reaction? Well, if you look at it, I've got about 3 or 4 times the amount of calcium chloride than I do of silver nitrate. Okay? And the silver nitrate is going to be consumed at twice the rate of the calcium chloride. All right? Now the good news is that the silver nitrate and the silver chloride, both of those are stoichiometrically equivalent. That means that I'm going to have the same number, the same molar ratio of silver nitrate that I do to silver chloride. Okay? Since silver nitrate is our limiting reagent, how many moles of silver chloride are going to be generated? I'll give you a hint. It's that number. Did you say that number? Good for you. All right, great. We're on the same page. So at this point, 0.00180 moles of silver chloride is going to be generated. Okay? Now just as an academic exercise, how much of the calcium chloride is going to be consumed? Right? Well, the ratio here of this one is 1 to 2. So it takes one of these to consume every two of those. So it's going to be half the amount of moles. So I'm only going to consume 0.00090 moles of the calcium chloride. So I've added way too much at this point. Oh well, it's cheap. That's the good news. Okay? All right, so that got the number of moles of silver chloride here. Now all I have to do is multiply it by its molecular weight. All right, so here's our conversion. This is the molecular weight of silver chloride. All right, and this is the number of moles that we got from up top. So if I multiply those two things together, I'm going to get out 0.25803 grams of silver chloride. Now the astute mind might notice that I have gotten, or I have too many, I haven't gotten, nice English phrase right there. I have too many sig figs at that point. Right? Now I've been using 3 sig figs for almost all of my calculations. So this is going to boil down to this 0.258 grams of silver chloride. All right? You see how that works? Whenever we do a gravimetric analysis or we do a titration, these types of concepts are always going to be basically the same. Okay? Find the number of moles, and if you line up the moles, you can find out which one is the limiting reagent. At that point, look for the limiting reagent moles, and that's going to control all the moles for your products in the reaction. Okay, let's see how this applies to acid-base chemistry.